So again, we are meeting for the second time of interaction for the course Vibration on Continuous System. In the first interaction, I have summarized the lectures that was finished before that date, and special problems or special queries that were asked by or raised by the learners was explained. Some of the doubts that were raised in live session questions or even the regular this question that is asked by the learners, although they have replied by email, but I tried to explain in the slide with equations. Today it is the second interactive session, and here I will first share some slides and summarize whatever is done between the period that first interactive session and today. Whatever modules are there in live that I will discuss, summarize actually. Detail has been given in the videos, so I will summarize these modules and questions given by some learners particularly for this live session will be discussed. So I have collected the question in the forenoon session, and then I prepared the answers. Wherever equation is required, equations are written, and then I will explain this to all of you. And if additional queries are there, you are most welcome to place before this interactive session, before me, and I will be pleased to answer your questions. So let me share the slides that I have brought for you in this interactive session. So this is session 2. Session 1 was conducted earlier in the month of February. So I'll summarize the completed modules. Completed modules are 5 to 8, and topics covered in 5 to 8 was specially on the vibration of beams and some special topics on vibration of beams, and also the state-based method. And then lastly, the module 8 is on the vibration of two-dimensional element that was membrane. So these are the topics covered between the modules 5 to 8. So question and answer, I have collected whatever is given in this Google Sheet by some of you, and then I will discuss this thing. So in question module 5, that is the week, 5th week, the 3 lectures were given, and in these 3 lectures we have discussed the natural frequencies and mode shapes of beams with different support conditions. Simply supported condition, cantilever beam, free beam, fixed beam. And before that, I actually derived the governing differential equation of motion using the Newton's second law, that is the force and moment balance here, and also by Hamilton's principle. So that I have discussed with the help of Hamilton's principle, it is possible to obtain the governing differential equation and boundary conditions simultaneously. Then I have proved the orthogonality condition of the transverse vibration mode of the beam. Here I am considering only Euler-Bernoulli beam, which neglects the shear deformation and rotary inertia effect. So orthogonality conditions of between two modes have been discussed, and this condition has been utilized in the partial differential equation of motion when we use the separation of variable technique to decouple the equation of motion. Decouple here means that equation of motions are converted into a time domain equation in discretized generalized coordinate. So in this sense, it is decoupled and it becomes a individual equation of motion, just like a motion of a single degree freedom undamped or damped system. So that is possible to solve very easily for any number of modes. For a particular modes, the solution can be obtained, and this will be identical. Only the number of modes and its characteristics, that means frequency and model vector eigenvectors, will be changed. Then once you get this discretized time domain solution for the kth mode, then you can use with the shape function, that is mode shape function, and can write the complete equation for the response, that is the transverse displacement of the beam. So the different boundary conditions influence the mode shapes, as you are clear in the earlier classes and also in the lectures that have been given. The most important parameter is lambda, that is the frequency parameter, and it is related to m omega square by ei, that is lambda to the power 4 is related to this quantity. Ei is the fractional rigidity of the beam, m is the mass of the beam, and omega is the natural frequency of the beam in radian per second. Now, the solution of the free vibration equation, that is found from the separation of variable technique in this way, that is, if I write this solution, that was the equation d to the power 4 pi dx to the power 4 minus lambda to the power 4 phi equal to 0, where phi is the mode shape function. The solution of this equation yields this expression, that is phi x is equal to a1 cos hyperbolic lambda x plus a2 sin hyperbolic lambda x plus a3 cos lambda x plus a4 sin lambda x. So you can see the mode shape is a combination of hyperbolic function and trigonometric function. Now imposing the proper boundary conditions at the ends of the beam, if it is a single span beam, two ends we apply the boundary conditions. For example, it is simply supported beam. That simply supported beam is designated sometimes as pin beam. It is written as pin hyphen pin. That means both ends are pin. Sometimes it can be written in some books P and PN. So that means both ends of the beam are fixed. It indicates. Suppose a beam is fixed, then we can write fixed hyphen fixed or CL hyphen CL. That is CL means clamped. So it indicates both ends are clamped. So imposition of boundary condition leads to a transcendental equation of this nature. It is a highly nonlinear equation which gives the multiple values of the roots lambda l. So lambda l is found as n pi, where n is n varies from 1 to infinity. Okay. That means for continuous system like that we are considering, it indicates that it has infinite number of natural frequencies and accordingly infinite number of the transverse mode of vibration or mode of vibration. Suppose if we consider the fixed beam, then the same solution, general solution that we obtain, we consider this to find the natural frequencies, but the natural frequency has to be found from the solution of this characteristic equation. So for so now I am talking about the fixed beam. Simply supported beam, the equation was very simple. That is sine lambda L, which gives this equal to 0, which gives the solution as lambda L equal to n pi. N varies from 1 to infinity. But here you get the equation in the form of cos hyperbolic function and trigonometrical function. And its solution can be obtained by various numerical techniques. Standard techniques are available. And in many textbooks, the frequency number lambda L is tabulated. So suppose pin beam, simply supported beam, in first mode, these are the frequencies. First 5 frequencies I have written for the different types of beam. First row gives the frequencies in pin condition. That is, we know that in lambda L here is 3.1415. Like that it goes. So lambda square is actually pi square there. It is equal to pi. Then clamp free is cantilever beam. whose first frequency parameter is 1.875. So these are very common thing. That is pin beam is simply supported beam is very common, for which lambda L equal to 3.1415. And for clamp free beam, that is a cantilever, one end is clamped, other end is free. So for that, the frequency parameter is 1.875. So like that in my slide, as well as in many textbooks that I have prescribed in the course syllabus, you will get the frequency roots. Now, what we'll do with this frequency? Frequency is a very important parameter in dynamic analysis, natural frequency. Because to understand the resonance phenomenon and to design the structure that will be away from the resonance of the condition when it is excited by possible sources. That condition can be achieved by properly designing its section, that is properly imparting its stiffness properties and the mass distribution, so that we get the frequency that we desire. Because it should not be close to the natural frequency of the possible excitation. So therefore, frequency is very important parameter. It is also needed if we use the model superposition technique to solve the force vibration response. So in the model superposition technique, when we apply this model superposition technique, the beam displacement yxt is represented as summation phi kx theta k t, and k varies from 1 to infinity. So this expression that you are seeing here is a very powerful expression, and then it gives the mode summation. So because of the orthogonality condition that we have written here, and you also know that it is proved using the mathematical techniques, that condition says that if I is equal to j, then product of the mode shape in two different modes. That means phi I x is the shape function or displacement shape of the beam at the ith mode, and phi j of x is the displacement shape of the beam at the jth mode. So if this product is made and it is integrated from 0 to L, of course mass is there here as a coefficient, and this result of this integration is 0. If these modes I and j are different, that means you can take it, say, first mode, and then here you can take second mode, or you can take, say, second mode, here you can take fifth mode, anything. So I should not be equal to j. If this condition is met, then we get 0. This integral value is 0. Otherwise, if I is equal to j, then you will not get 0, but you will get a non-zero finite number. That number is sometimes called a generalized mass. And if I normalize the mode shape such that the generalized mass is 1, then we get that result of this integration m phi square x dx equal to 1, where this phi ix is the ith mode shape. So as a result of this, we get this normalized mode shape. So now concept of normalized mode shape comes. In many occasions, mode shape is normalized with respect to mass, so that it becomes this a multiplier which is root 2 by ml and sine for simply supported beam, sine k pi x by L. This is the kth mode shape. So kth mode shape is this. So this is the mode shape coefficient. √2 by ml that you are seeing, it is a coefficient. Otherwise, you can see the mode shape magnitudes cannot be determined in absolute sense. These are all relative. So the magnitude that we get or amplitude, we have to normalize it. So this normalization constant for simply supported beam of constant mass m is written as √2 divided by m. And if these mode shapes are used with this coefficient, then we get this integral equal to 1, because the integration of this sine n pi x by L dx 0 to L is always L by 2, because sine and cosines are orthogonal functions. So similar things also happen with cosine function. So if I use that phi I equal to this √2 by ml into sine I pi x by L, then the result becomes 1. So we write the orthogonality condition in this way. Now, in the module 6, we utilize the orthogonality condition and the modal superposition, this modal superposition equation, to decouple the equation of motion, and then we solve some problem where the beam is excited with some force. And then we also discuss the response of a beam subjected to moving load. So decouple equation by making use of orthogonality conditions and mode superposition technique, we get for a particular mode, ith mode. So I is equal to, actually I can vary here. I varies from 1 to up to infinite number of modes. But theoretically, we can truncate the modes. We have to truncate, because up to infinity we cannot go to sum up. Therefore, naturally we consider the mode number, say n modes to calculate the response. So we can see this is similar to the single degree freedom equation of the damped oscillator. Okay. So solution of this is easily known. We know already from the basic lecture that I have given in the first module. But what question comes, what is Qi? Qi in the process of orthogonalization, it becomes like this. Fxt is the distributed force on the beam. Actually, when you consider the partial differential equation of a continuous system, the external force is treated as a distributed force. That is, it is a continuous function and its derivative exists. Therefore, if xt is a distributed force, then fxt into phi of xi, that is the mode shape function, when integrated with respect to x, will give you the generalized force in time domain, because we are integrating with respect to L, and therefore only the parameter t will be involved in the final expression. Then after finding this generalized force, we can solve this equation by the known technique. If it is a harmonic force, you can know how to use the expression for the steady state response. Or if it is a, say, step input, you also know how to use this expression for the step input. And for any other arbitrary type of excitation, you can use the general procedure, that is the Duhamel integral. Then when you find out this eta it, that is the generalized coordinate, the complete response you can write at any location x, at any time instant t, is summation of mode shape function into generalized coordinate in time domain. So we can find like that. Now, question is how to consider the concentrated force in expression of generalized force. In many occasions, force may be acting only at a certain locations. For example, some reciprocating machine is installed on a floor beam or a floor whose vibration is transmitted at some point on the beam, supporting beam. So in that case, beam is subjected to a harmonic force at certain point. And say T is the force that is acting on the beam at a certain point. For example, if I have suppose we have a beam here and we have a force P here at a distance A. The length of the beam is L. So in that case, distributed force Fxt on the beam should be written like that, P into direct delta x minus A. Because the force is acting only at this point, x is equal to A. In other point, no force is there. Therefore, we have to replace this Fxt by this. That means here, instead of this Pt, we write Fxt. And Fxt is nothing but this. So if I write, say, full expression for this, we can write P phi I x delta x minus A dt. P of t. P is a function of t. It may not be constant in many cases. So in that case, you will get a integration that requires to be evaluated using the property of direct delta function. The direct delta function is very important property that this property is conveniently used in many physical problems. So if direct delta function is multiplied with other functions, say fx, and then it is integrated with respect to x between any limit minus infinity to plus infinity. These are two extreme cases, but in practical situation, this value will be finite. So the integration is nothing but the value of the function at this point where direct delta function is defined. So that means fx, this integration fx direct delta x minus a dx between any limits will be only the function evaluated at a. So that is very simple property. Suppose here P is a constant force and phi x is the mode shape function of a beam. Then what we get this QIT as P is a function of t, for example, but phi is a function of x. So phi is now replaced, x is now replaced by a. So we get generalized force like that. That means phi I of a is a constant term. So this becomes a function of time t. So generalized force in ith mode is calculated here. In the process of finding generalized force here, we use the mass normalization, that is normalization with respect to mass. It simply means, therefore, generalized mass is 1. Otherwise, if generalized mass is not 1, that QIT should be divided by a quantity which is generalized mass. Now, considering the homogeneous part of the solution that exists due to initial conditions, we write the complete solution as this. This is the mode shape function multiplied by the time function. So time function contains, this is the homogeneous part for a damped system. And this is particular integral Particular integral means due to this particular integral that is due to external force that you have to found. And for linear system, it can be superimposed. So in this way, we get the complete solution. Now you can see here the response. Now you cannot plot because you do not know A and B. Although you can know the particular integral for a certain type of excitation, say it is a state harmonic vibration, so steady state expression you know, or it is a step function, you know the expression. But A and B, these two constants of integration have to be known. So how you know? Apply the initial conditions, and then you will be able to get this constant A and B. Now applying the initial condition, that is if you put t is equal to 0 here in the expression of y and y dot, that means velocity, you will get two equations containing A and B. And then from that you can solve the constants for the constants A and B. So similar concept is used for the problem of being subjected to moving load. This type of problem is very often met with the vibration of beach due to moving wave. So suppose here for simplicity we are considering a single wheel load that is passing over the beam at a velocity v, constant velocity v. So as per our earlier theory, the fundamental beam theory that we have developed here for inner Bernoulli beam vibration, we write this equation eta dot it plus 2 xi omega I eta dot it, eta double dot it, that is the acceleration terms. Then 2 xi omega I eta dot it plus omega I square eta it. And this is actually the generalized force. This term is generalized force. So this is Qy, and it is found from this integral. Now here generalized mass we have not used for the normalized mode shape. So we are keeping here the generalized mass M, capital M. So integration 0 to L, and force is P. Okay, and it is acting into this phi I of x, and phi I for simply supported beam is nothing but sine I pi x by L. That is the mode shape function of a simply supported beam that I've written into direct delta function delta x minus at any time instant t. The location of load P is V into T. So I write x minus Vt. Then integrate it between the limit 0 to L. So you get now this generalized mass, say M, for this condition is normalized mode shape is not used. Then we write this integration 0 to L M phi square x dx. And you know that if it is a sine function, then it is integration of this phi square x dx will be L by 2. So generalized mass is ml by 2. So therefore we are getting ml by 2. That means 2 goes to the numerator and p is there. And then we are getting, instead of x, we have to replace it by vt. So that means this term that I'm blocking here with a square box, a rectangular box, it is sine omega it. How omega it is coming? Omega I is coming as I pi d by L. So instead of x, we have put this Vt. So I pi b by L is plugged together and it is giving the frequency. So you can see sine omega it term is coming. So therefore, constant moving load gives a oscillatory load that is just a harmonic function, and it is happening in case of simply supported beam. So in beam vibration, specially subjected to moving load, we use this concept to analyze this response and subsequent derivatives of the response and dynamic evolution. Other special topics that I have discussed in the module 6 are vibration of beam on elastic foundation. That thing is very common, especially this say railway track rails supported on sleeper continuously at a close spacing. Its sleeper acts like a spring. Model like a spring. So that means this beam is resting on elastic subgrade. So elastic foundation. So the equation of motion, this is beam, this is elastic foundation or elastic subgrade, sometimes we call in case of pavement. So equation of beam is modified by including this expression ky xt. This represents the spring force, additional spring force. That means the net load on the beam that is acting here as fxt will now be reduced by k into y. Y is the displacement of the beam and ky is the force on the beam. So the ky is now transferred to the left hand side, and it is equation now contain this three terms for undamped system. Natural frequency of such a beam is higher because of this additional stiffness that is imparted by the elastic foundation, and you can see the contribution of this is k by n. Then we consider the effect of axial force on the vibration of beam. In many cases, beams are axially compressed. In addition to transverse load, the beam is also compressed in axial direction. So in such a cases, the equation of motion is modified, taking account of this axial force. So in that case, we considered a free vibration case here. And you can see that free vibration case that no force is there in the right hand side, and this p del square y by del x square is the contribution of the axial forces. Now for that, the frequency equation that is written as omega n is equal to omega ns. We are considering a case of simply supported beam into root over 1 by some ratio of the load. So this load ratio is nothing but the axial load that is acting to the Euler buckling. Now for a simply supported beam, Euler buckling load is pi square EI by L square. So this P by PE is the Euler buckling load. So if say P is very small, the axial load is very small, then P by PE can be neglected. So in that case, the natural frequency of the beam will be same as the natural frequency of the simply supported beam. Otherwise, depending on the ratio of the P by PE, we can find the natural frequency of the beam, which is actually compressed. In module 7, we discussed the beam with multiple concentrated mass at arbitrary location, because the closed form solution of the beam carrying a mass at the end is well known, and that is found from the exact solution of the differential equation after imposing the boundary condition. But for the beam which carries number of concentrated masses at arbitrary location cannot be determined so easily with the analytical means. So here I have discussed a semi-analytical method based on some research paper I have referred in this video, and also today also I have given the reference. You can search it. And then I have discussed the state-based method of solution in vibration problems. And then some of the problems with beam with moving oscillator, pulsating force, and rolling mass was discussed in the module 7. So a beam when carries number of concentrated masses, say M1, M2, up to MP at any arbitrary locations. So M1 is situated at X1, M2 is situated at M2, like that. Now here you can see, suppose for example here we neglect damping, then equation of motion can be written as EI del 4y by del x4 plus M del square y by del t square equal to minus J equal to 1 to P, that is summation 1 to P, Mj del square y by del t square delta, direct delta x minus xj. The direct delta is used to specify the location of the concentrated mass. Now here you can see this term is nothing but the inertia force. So effect of concentrated mass can be treated as an inertial reaction in the beam. And if it is transferred to the right hand side, it represents the force vibration equation of the beam. Now this term is analogous to a term that is used in force vibration analysis. So that is nothing but your say FXT. A forcing term. So then this equation is decoupled in the same way that we have done earlier. And the eigenvalue solution is developed in this form. Some algebraic manipulation you have to do it. So you can see the eigenvalue problem is like that. Small omega square by capital omega square minus say B matrix this omega eta bar is the generalized coordinate, and this if omega is the natural frequency of the beam without concentrated mass, and capital omega is the natural frequency of the beam with concentrated mass. Now here we use the approximate mode shape function, not approximate, actually the exact mode shape function of the beam which do not carry any concentrated mass. So for that, the exact solution for the mode shape function is known. So this shape function is used to formulate the eigenvalue problem. Therefore, it is not exactly analytical method. It is called a semi-analytical method. The B matrix is found as the sum of the unit matrix plus another matrix that is formed as the product of this the two vectors, model vectors multiplied by the concentrated mass. And you can see that for non-trivial solution, the determinant of this matrix can be equated to 0, and we get the frequencies and corresponding mode shape. So we have seen that, and also the researcher who has published this paper also validated this method with number of analytical closed form result available in this textbook. And this method was working fine, at least up to 5 mode. This result was giving almost close to the accurate result, exact result. In the next chapter, I discuss the state-based method, but before that, I want to discuss why the state-based method is necessary. There are various opinions that why the state-based method factors to be selected. Many people do not prefer the state space method. Some people prefer, especially the researcher or the engineers who are working with the vibration control, active vibration control. They usually prefer the state space method because in that case, the control toolbox available in the MATLAB can be used. Now, for linear dynamic analysis, damping can be assumed as a linear combination of mass and stiffness. So for that assumption, we can get the C matrix, that is the damping matrix for a multi-degree freedom system, is equal to some constant into mass matrix. So that constant has been found as 2 xi n omega n. Okay. From that equation, we can get the damping in the nth mode is equal to A naught divided by 2 omega n. Now, when one assumes that damping is proportional to stiffness, then equation can be written as C matrix equal to A1K matrix. A1 is the constant of proportionality, and we can find out that the damping in the nth mode is nothing but A1 omega n divided by 2. So combining this mass and stiffness proportional damping, one can write that the damping in the nth mode is nothing but the constant, unknown constant A naught divided by 2 omega n plus A1 omega n divided by 2. So omega n is the natural frequency in the nth mode and xi n is the damping ratio in the nth mode. So consider any, because two constants are here, so we require two equations to solve these two unknown constants. So consider any two modes, say first mode and second mode, or second mode or third mode, anything. Then you can find the constant A naught and A1. Once you find the constant A naught and A1, then you can find the damping matrix completely as a linear combination of mass and stiffness matrix. This type of matrix is known as Rayleigh's damping. Now here you can see the damping matrix is constructed based on this assumption that it is proportional to the mass and stiffness. That assumption is now a shortfall in the dynamic analysis because in many cases this assumption may not be valid. So what to do? How to use the general case of damping? Of course, we are confining our discussion within the linear range of damping. Hence, there is a necessity of state-based method, even if you use the analysis for linear system. So here, consider a second order equation where C is the damping matrix and K stiffness matrix, M is the mass matrix. The damping matrix can be found as a linear combination of M and K that I have discussed, and this second order equation can be solved. But here you can see this assumption is must. Otherwise, you cannot decouple the equation of motion. So what is done here in state-based method, the equation of motions are transformed into first order equation. Writing the state vector, say y. Y is a state vector. Introducing the state vector. State vector has two sets of values. The first set, say y1, contains the displacement, and the second set contains the velocity. So it becomes 2n cross 1 vector size. So other equation, say A also becomes 2n by 2n size. Now you can see the A matrix is augmented. The augmented A matrix is here. You can see here it is a null matrix, but its size is n cross n. It is unit matrix. Its size is n cross n. Here it is a matrix minus M inverse 1 into K. So that is n cross n, and that is minus M inverse into C. That is also n cross n. As a result, this matrix is 2n by 2n matrix. So straight space method is a first order method that we solve the first order differential equation instead of second order differential equation. But the matrix that we get for the eigen solution is a matrix which is unsymmetrical. As a result, we are not getting the real eigenvalues. Instead, we are getting the eigenvalues which appears in complex number, but they are complex conjugate. So let a pair of complex eigenvalues are like that. Say lambda k is an eigenvalue which is given as minus j k omega k plus I omega k root over 1 minus j k square. Similarly, the next value, which is the conjugate of this lambda k, is minus j k omega k minus I omega k root over 1 minus j k square. So from this equation, it can be seen that omega k is nothing but real part of lambda k whole square plus imaginary part of lambda k whole square. Then damping ratio is minus of real part of lambda k divided by this real lambda k whole square plus imaginary lambda k. So negative real part of eigenvalue. The eigenvalue has two parts, complex conjugate eigenvalue, complex eigenvalue, real and imaginary. So if we get the negative real part of the eigenvalue, the system is stable because our decaying factor is exponential to the power minus chi, that is the damping ratio into omega into t. So if chi is a positive quantity, and it becomes when the real part of eigenvalue is positive. Now we find the this mode shapes and natural frequencies appearing as a complex conjugate. The complex natural frequency indicates two parts. One is frequency part and another is damping part. So simultaneously we get the two parts of the model characteristics. Then we discussed being with a moving oscillator. Say in earlier cases we discussed a moving load, which is a constant moving load that was not oscillating. But here you can see that a oscillator, which is also oscillating in the vertical direction. Z is the displacement of the mass. And you can see here, due to this displacement of the beam, the relative displacement is experienced by the spring and the dashpot. So therefore, the force that is imposed on the beam depends on the mass displacement as well as beam displacement, as well, and also the damping and stiffness properties of the oscillator. So here you can see that although we have the equation in this fashion, the forcing term that fxt, if we neglect the damping, say C0. So in that case, we get K into Z minus Y. And then the constant load part, that is the static part, is also added here into direct delta X minus BT, because the position of this load is now depending on velocity V. If C is also taken, then another term would have been there, C into Z dot minus Y dot. So relative velocity into damping of this oscillator, that will give this. So the combination of these two, that is the damping stiffness of the oscillator into relative displacement, will give the spring force, plus the damping into relative velocity of the damper will give the damping force. These two forces together, added with the static load, will give the force induced on the beam. So beam is subjected to vibration due to this load. But you can see the beam vibration also affect the oscillation of the mass. So these two forms a coupled system of the coupled dynamics, forms a coupled dynamic system. Then in the eighth module, we have considered the vibration of membranes. Membranes is a two-dimensional element. So we are getting XY coordinate in the differential coordinate differential equations. So differential equations is a partial differential equation, but it is involving X, Y, and time, T coordinate. So we will obtain the differential equation in rectangular coordinate system. Then we have discussed the eigen solutions of rectangular membranes. Then we discussed circular membrane. An equation of circular membrane was found in polar coordinates because polar coordinate is very suitable to solve the problem of circular elements. But here, of course, we are considering the symmetrical element, circular membrane. So therefore, here the axisymmetrical element is considered. That is the axisymmetrical operator in polar coordinate was considered. Eigen solutions of the circular membranes are obtained and different characteristics of the modes was also shown to you. The equation of membrane was obtained as this T del square W plus Q equal to rho this del square W by del T square. Now this del is a Laplacian operator. This is Laplacian operator. Del square by del x squared, del square by del y squared. So as a result, we get the equation both in derivative of x and with derivative of y. And the right hand side of this equation is the inertia force. So this is the inertia force. Inertia force rho is the mass per unit length. Not per unit length, per unit area. For a membrane, because it is a two-dimensional element, so we are specifying all these parameter per unit area basis. So this equation will be satisfied by a solution that can be found, and also it should also satisfy the boundary conditions. So boundary condition for the supported membrane is W is 0 at the supports, and also at any point on the membrane located on the edge of the support, that vertical component of the tension that you are seeing here, vertical component of the tension is 0. So these are the equations that require to be satisfied along with the differential equation. We found the general solution of the membrane equation for free vibration, and mode shape was found as a combination of two sine functions, sine alpha x, sine beta y. And as a result, we get frequency parameter as this omega n, mn. Here, two index are actually assigned. Two index are assigned. Omega mn for the frequencies, and we get the natural frequency as c pi root over m square by a square plus n square by b square. And mode shape function is simply the combination of two sine terms. Sine function in x direction, sine function in y direction. And we have seen the mode shapes of the membrane for a particular length to breadth ratio, that is called aspect ratio. Here, say fundamental mode is 1,1. So here we get the half waves that is formed in each direction is only 1. That is the fundamental mode. But here in the mode 1, 2, we find that one half wave is formed in the x direction, but two half waves are formed in the y direction. So therefore, one nodal line is seen here. In the mode 1, 3, we see that one half wave is formed in this x direction, but these three half waves are formed in this. Two half waves are formed. Two half waves are formed in this y direction. So like that, you can continue with the mode shifts. Okay. Then we have come to the circular membrane. As I told you that equation for circular membrane is very convenient to solve using the polar coordinate system. So Laplacian operator in polar coordinate system is different. But if I consider the axisymmetrical condition, then these quantities are independent of theta. So therefore, derivative of all quantities with respect to theta will be 0. So therefore, the Laplacian coordinator will be in this very simple form. Very simple form. Laplacian coordinator for axisymmetrical condition is this. Other terms need not be considered. So we get the characteristic equation to find the natural frequency in with a very special function, mathematical function, that is known as Bessel function. And Bessel function is a oscillatory function. Roots of the Bessel function will give the natural frequency. Now Bessel function, there are two kinds, Bessel function of first kind and second kind. Bessel function of first kind need not be considered because it will give the unbounded solution. So therefore, we consider unbounded solution at the 0 value, m is equal to 0. So therefore, we do not consider it. So we take the Bessel function of the first kind only. Bessel function of the zeroth, that is first kind. Okay. Now you can see that mode shape, these frequencies are nothing but the roots of the Bessel function. So first frequency that is found from the Bessel function of the first order of zeroth, Bessel function of first kind of zeroth order, there is the fundamental root corresponds to 2.405. Like that, 5.520, like that it is. Then this first order, it is zeroth order, then first order, we find that this is the 3.832, because in the mode shape function of two-dimensional element, we generally find that two index that are associated with the omega. Omega suffixed by two parameters, m. So therefore, one represents this quantity and another represents this quantity. So the roots of the Bessel function of first kind will now yield the infinite number of roots. And the solution of the frequency is very simple. Omega mn equal to c into beta mn, where c is the wave velocity. C is the wave velocity, that is equal to root over T by rho, where T is the tension per unit area. So we have symmetrical modes as well as asymmetrical mode, antisymmetrical mode. Nodal lines are formed in a diametrical direction as well as the circular nodes are also formed. So nodal lines are circle in case of symmetrical nodes. It's some distance at r is equal to r1, and straight diametrical lines are also formed at theta is equal to theta 1. Now here you can see that when we consider the natural frequency, say omega 01, then for m is equal to 0, there is no diametrical nodal lines. Here you are not seeing any diametrical nodal lines. And there is n minus 1 circular nodes. But n is equal to 1, there is also no circular nodes. So here for M01, that is the frequency corresponding to this nodes 01, there will be no nodal lines. So omega 01 is 2.4048 C by A. Similarly, when you get the frequency m is equal to 0 to 0 and n by 2, we get for m is equal to 0, no diametrical nodes. But for n is equal to 2, we get 2 minus 1, that is one circular node. So one circular node you can see here. Similarly, for n is equal to 3, we get this n is equal to 2, that is 2 minus 1, we get one circular node. So one circular node you can see. Here you can see for n is equal to 3, we get two circular nodes. So one circular node you can see here and another circular node you can see here. Unsymmetrical nodes are modes are formed when the index m is other than 0. So m is equal to 0 always indicates the symmetrical modes. So m is equal to 1 and n is equal to 1 is the unsymmetrical mode. And then you can find that for m is equal to 1, there is just one diametrical nodes. And for n minus 1 circular node. And for that, there will be no circular node because n is equal to 1. So the natural frequency omega 11 can be found as 3.8317 C by A. Like that, when m is equal to 1 and n is equal to 2, you will get this circular node, that is 2 minus 1, that is one circular node can be seen here. Okay. And one diametrical node is already present. So at any distance, this circular node can be located by this relation Rk equal to beta mk divided by beta mn A. Now here you can see for that position, that is m is equal to 1, n is equal to 2, we can locate the circular node by this ratio, that is 3.8317 divided by 7.0156. So circular node is located here at a distance of, if you calculate this ratio, it will be approximately 0.55. So some questions are raised in the Google form that I have collected. First question was regarding the selection of state space method. I have not written the full question, but the thing that is asked in the question is why the state space method was selected. Because it gives a complicated method of solution, complicated eigenvalue, complex form, difficult algebra. So why to select this thing? But there are certain advantages that I have listed, and therefore people prefer this state-based method of solution also. So reasons are the order of differential equations are reduced. So from second order, it is reduced to first order. So therefore solutions are simpler because for first order system, the impulse response function is also simple. The complex frequency response function is also simple. Then displacement velocity that constitute the state vector are obtained simultaneously. There is no need of finding the velocity after differentiating the displacement because you are getting the solution in a vector form for the displacement and velocity together. Then the assumption of proportional damping for model superposition technique need not be used, because here the dynamic matrix for finding the eigenvalues are augmented to a size of 2n by 2n. So therefore, this assumption need not be made. Complex eigenvalues with negative real part also implies stability of the system. And lastly, also I can tell that this method can be used for active control, vibration control of the structure. Then second question was there on the same state space method, why the eigenvectors are complex. Eigenvectors are coming complex because of the matrix are the A matrix that we are finding, that is unsymmetrical. So no real eigenvalues are found. Some eigenvalues may be real, because in that case the imaginary part is 0. That means it indicates the rigid body mode. If some system has the combination of rigid body and flexible modes, then some eigenvalues may be only real. So that indicates that imaginary part is 0. That means frequency is 0, that is having the rigid body modes. Then how the real mode shape can be plotted? You note that eigenvector corresponding to is some size, and there also exists a conjugate form of it. The addition of complex number and its conjugate is real, because we know when the two complex number are two complex number, one is conjugate of other, is added, we get a real number. So therefore, if two sets are added, we get a real eigenvalue. Of course, the magnitude is arbitrary, but we can normalize it with a suitable procedure, and then we can plot the shape. How the constant moving load imposes vibratory loads. So in a simply supported beam subjected to moving load, we have seen that the generalized force is given by this expression. P phi of x into delta x minus a, where the a is the position of this moving load measured from one end, and a this at any instant of time t, the x is measured as velocity into time. So therefore we get this pi I x is equal to sine I pi x by L. And as a result, we get the QIT equal to P sine omega it. So this imposes the vibratory load. Then last question is how many modes are to be considered for accurate prediction of dynamic amplification factor? If we see the expression that is derived, we can see that displacement contains a term 1 by I to the power 4. Bending moment contains a term 1 by I square, and the shear force contains a term 1 by I, where I is the number of moves. Now, from this expression, the inspection reveals that the displacement series is very rapidly converging, because it is I to the power 4. So very few terms are needed for accurate prediction of dynamic amplification factor. However, the number of terms increases as we go on higher derivatives. So bending moment requires more terms, shear force, displacement, and finally shear force requires again more terms compared to bending moment. So for displacement, first term is sufficiently gives accurate result in many occasions. Wherever the bending moment, dynamic amplification, and shear force dynamic amplification can be obtained accurately with more number of modes. Thank you very much. Is there any question on your part? I have not seen in this yet. So now it is. You can also ask in a discussion forum. I will answer. Okay, thank you very much.